So what we'll discuss this session will be about the shortest path in a graph. And basically, we'll learn a new method that is named breadth first search. But to understand this method, we'll start by looking how we'll do the same operation with depth first search. So let me start by considering a graph. And I will consider a special type of graph. So it will help us to show the difference between depth first and breadth first. And I will consider a small graph just for the sake of example, so it will be easier for us to do all the computation. Let's say that we have just 5 vertices, and we have the following edges, and so an edge from 0 to 1, from 0 to 2, from 0 to 3, and from 0 to 4, and also edges between these between all the vertices. Now, what we'll do, we'll also draw the graph that is given by these two sets. So sure, it's a pretty straightforward graph here. So if we put 0 in the middle, and I'll make this a little bit smaller. Then we can put the other okay, kind of is not perfect. One, two, three, and 4. And sure, we can link all of these with lines. Let's make this a little bit bigger. Okay, so this is a special type of graph. It's not a very complex graph, but it will serve our goal of showing the difference in between the depth first and breadth first methods. Now, let's define the problem that we want to solve. So it's the shortest path given two connected vertices, determine the shortest path between them. And sure, this is a very useful problem because many times you will like to take the shortest path between 2 points to arrive there faster. And this graph is not serving us very well because it has trivial solutions. So if we look at this example, we'll say easily that if we want shortest path between 0 and 1, it's just the road from 0 to 1. Now, if we want shorter space from 1 to 3, it's a little bit more complex in the sense that and has actually 3 solutions, but I don't ask for all solutions. I'll ask for one solution. So one solution is to go 1, 0, 3, and another solution might be to go 1, 2, 3, and the last solution is to go 1, 4, 3. So all of these will give us the shortest path between the vertices 1 and 3. Now, the goal for today is to find the algorithm to determine this. And as usual, we'll do it first simulating it, and then we'll look at the code that is performing the same operation. So let's start by trying to apply depth first, the method that we apply for connected components, and trying to apply the same method here to compute the shortest path. And we'll assume the representation with which we start. So we'll assume adjacent link list representation, and let's so to create the representation, we'll use very similar. So we'll have a number of vertices is 5, and we'll have adjacent lists. Will be an array of arrays, and basically we'll have the following subarrays. For 0, we'll have, and we'll keep them in order 1, 2, 3, 4. Then for 1, we'll have 0 to 4. For 2, we'll have 0, 1, 3. And for 3, we'll have 0 to 4. And for 4, we'll have 0, 1, 3. So these are representations that we use in the previous guided activity. Will keep the same. Now, if we want to apply depth first search for this representation and graph, what we did before was to use marker to show that we pass through a node or not, and also to use to count how many elements are in the connected component. Sure, here we have other goals. So here we'll use a different type of so depth first search for shortest path. And we'll start with this representation here. And I will make this shorter just to enter easier. Okay, so now to apply depth first search, sure, let's say we start from 0 and we like to compute the shortest path to all the other elements. And I will present you a method. It's not trivial, but it's not very complicated. So what we'll use besides the marker to see if we pass through a node or not, we'll use two other arrays. And let me present those arrays. Trying to find now a good way to insert the arrays. So let's put here, and I will show this how it works step by step. So let me look in the code actually for a second to use the same names. So it will not confuse you when you see the code. So let's we'll have the marked array of booleans. So this will be like initially everything is not marked. So everything is false. Then we'll have through array that will show us the shortest path through what nodes arrive in a given node. And -1 means we don't know yet. And we'll have the size array, the length of the path. And again, this will be 0 initially because we haven't computed the path yet. Now, the problem that we'll solve will be to start from source. In our case, let's start from 0 in the first example, and then to compute the path to all the other nodes. Now, this is trivial one because 0 is linked to all the other nodes. But let's see how the depth first method works. And we'll follow the same rules like for the depth first that we did connected path. So how this will go? So we start with, let me put this one here, add a new text area. So we'll start with depth first search for 0. And sure, 0 is not marked. So we'll mark 0 as true. And then we'll go and check all the adjacent elements of 0. So in our case, the adjacent elements will be 1, 2, 3, 4. And for each of them, if they are not marked, we'll call recursively the depth first search. Now, when we make this recursive call, we'll also want to be sure that we mark the path to arrive in that place. So let's check first for vertex 1. Vertex 1 is not marked, it's false. So I will consider it. And I can say to go to vertex 1, I will come from vertex 0, and the size will be 1 because to go in vertex 0, I have 0 size. And now to go from 0 to vertex 1, I add a new link. So the size will be 1. So doing that, then I can call recursively to look at depth first search for the vertex 1. Now, this one, what we'll do, will apply recursively the same method. So it's looking, is one, I know that one is not marked because I came here, so I will mark one true. And now I'm looking at all the adjacent elements of 1. And in our case, 0, it's marked, so I do nothing. 2 is not marked, so what I want to do now for 2, I can say, okay, 2 is the length to go to 2 will be the length to go to 1, to which I add 1 because from 1 to 2 I go to another area. So the length to the size will be 2, and I will come to 2 from 1. And then I can go therefore search in 2. Now, reaching 2, again, I will need to look at all the adjacent elements. First of all, I will make 2 true, and I need to look at all adjacent elements of 2, which are 0, 1, 3, and 0 is marked. I don't want to do anything. 1 is marked. For now, I don't do anything. But 3, it's not marked. So what we'll do, we'll go depth first search in 3. And we like to repeat now the same procedure for 3. Sure, when we go there, we want to update the way how we arrive there. So I went to 3 from 2, and the size will be the size to go to plus 1. It will give me 3. So now, arriving in 3, I will do the same kind of depth first search in the sense that I'm looking at the, I mark first 3 with true, and I'm looking at the adjacent elements of 3, 0 to 4, and I will look at all of them. 0 is marked, 2 is marked, 4 is not marked, so I will call recursively depth first search of 4, but before that, I will update my path to 4. I'm coming to 4 from 3, And the length will be, because I went 0, 1, 2, 3, 4, the length will be 4. Now, and sure, I call depth first search of 4. Now 4 has the adjacent element 0, 1, 3. So 0 will be marked, do nothing. 1 will be marked, do nothing. 3 is marked, I do nothing. And this finalizes the first round of going through deep, as deeper as I can with depth first search. Now, after I finish this, sure, the method is, okay, I finish with 0, 1, 3. Now I want to go back and see how I will continue this from node 3. But for node 3 also I consider 0, 2, and 4. So basically all of these are considered. So let me duplicate this slide. And what I will do now, I will just delete all of these because I consider all of them and come back to 2. In 2, I have 0, 1, and 3. And again, I finalize everything for 2. So I can say, okay, 2, it's also finalized. So here I started from 1. I went to 0 to 2. Next one is 4. And you'll say, okay, 4 is marked, so I don't need to go in 4. However, 4 must be marked. I forgot to mark, but must be marked. However, my path to 4, the size of my path to 4 is 4 because I went 0, 1, 2, 3, 4. If I go 0, 1, 4, the path to 4 will be only 2. So basically, the road to 4 through 1 is much better than the path to 4 is shortest than going all around. So because of that, just the test that is marked is no longer useful. So if it's not marked, clearly I want to go there. But if it's marked, I need to look, do I have a better choice if I go through that element? So, always I need to make this test, even if it's marked. So it's marked, but I also want to check if going 0, 1, 4, it's a better path, and it is. It's giving me only 2. So, and it's better path. So what I will do here a DFS of 4. So doing now, again, deciding, okay, I will try to go depth first through these 4. I'll repeat now all the computations. So first of all, I need to say, okay, if I go from 1 to 4, so if here I am coming from 1, my path will be 2 plus 1 plus 1, 2, because going to 1, I have the size 1, adding 1 more, it will be 2. So now this will be better. But going to 4, I'll need again to look at everything because now I may have better path to go there. So let's look if my path to, so I have here 0 and sure, 0 is a source, so I don't want cycles. And it's marked, so this will not give me a better path because the path to 0 is 0. It's starting from there. Now, going from 4 to 1, again, it will not be better because 2 plus 1, the size will be 3. It's like going 0, 1, 4, 1, the size will be 3. I already go with a size of 1. So mark not better path. So I don't want to go there. And going in free, I have, it's marked already because I already went through free, and the path to free was free. And if I go through 4, I will get also free. So nothing better. So I don't need to go through free because it's not better. If it's as better as the previous one, it will just give me another solution. But I just want one solution. So basically what we did was to go through all of these. And the only thing that I improved this time was the 4. Now, following the same logic, and for one, I finish now all the elements. I have 0 to 4, all the adjacent elements. So what I will need to do is to come back to the initial call. I went to 1. Now I want to go to the next adjacent vertex of 0, which is 2. And 2, it's marked, but going from 0 to 2, it will give me a path of 1. So, which is better. So better path. So in that case, I want to update and go through 2. So in that case, to go through 2, I will come from uh, 0, and the size will be just 1 because I went directly through 2. Now, and sure, I will call DFS of 2 because now it's a better path. And as you can imagine, I can continue this, and the next thing that I will change will be free, because now going to free through 2 will give me only a path of 2, and will go through free. I will remain going through free through 2. So this will not change, but the size of the path now it's better because I go 0 to 3, which has a size of 2. The path has only the length of the path, it's 2. We can put here length just to be clear. And then I can do this again for 2. It will do a lot of depth calls. And after I finish, I will come back here and take free. And again, 0 free, it's a pass, and which means going to free is better to go directly from 0, and I will get the size of 1. And again, I will do all the depths first for free. After I finish, I come back to 0, and I do the same for 4, and I have a link here, and it will give me again 1. Now, I didn't repeat all these steps because they are redundant, but I wanted you to see how many calls this depth first search is doing, and in order to compute the shortest. So to apply the breadth first shortest path for another source, let's say 1, again, I will start from false. Initially, nothing is marked. And I don't know through what element they are coming. And the length will be also 0. Because I haven't computed anything. So basically, I want to see which is the shortest path starting from 1 and going to all the other elements. So first we'll put the source in the queue, and at each step, I take the first element from the queue, process it, and then come back to the queue. And if I still have elements in the queue, I'll take the next element and so on. So let's take the current vertex, which will be 1, and the queue right now it's empty. And I'm looking at all the adjacent elements to 1, which are 0, 2, and 4. So let's take 0. 0 is not marked, it's false. So first of all, taking 1, I will make it true. So 0 is not marked, it's false. And then means I can go from 1 to 0. So let's make now 0 true because I did it. Also, I come to 0 from 1, and the length now will be 1 because it's the length to 1, which is 0, and I add 1, I get 1. So this means this is a good next step. So I will put 0 in the queue. Next, I will go to 2 and do the same. I mark, because 2 is not marked, it's false. I mark 2 as true. And I will say, okay, I'm coming to 2 from 1. And the length to go to 2 will be 1 because it's coming from 1, which has a length 0, trivial. So then I go to 4, and I add 2 in the queue. Then I go to 4 and do exactly the same thing. And this will mean that I come to 4 from 1, and the length will be 1. And I put 4 in the queue. So now I finish all the neighbors of 1. Basically, you see that 0, 2, and 4 are marked as visited, and also they have direct connection with 1, so they are marked as having an element. Now, this means that I am ready to take the next vertex from the queue. Next vertex is 0, and 0 is having the following 4 adjacent elements. Now, 1, it's already marked. I don't want to go there. 2, it's already marked as true. I don't want to go there. 3 is not marked as visited. So this means 3 it's a good next step. So I will mark 3 as true. I'm coming to 3 from 0, and the length will be the length to 0, which is 1, plus 1 will be 2. Now, because this was a new element, I will add 3 to the queue because I want to be sure I am looking at its adjacent elements as well. Now, 4, it's already marked, so I have nothing to do for it. It's marked. Now, I will continue this, and sure, this will disappear, and I will take 2 from the queue now. But as you can see, all the nodes are visited. And because everything is visited, I can do this and check all the adjacent elements for 2. Then, but those will be visited. I will ignore them. Then I will take 4 from the queue, and all the elements are visited. So I will ignore this one as well. And the last, I will take 3 from the queue, but 0, 2, and 4 are visited. So I will ignore those as well. And now the queue is empty. which means I finalize the search. So as you can see again, the computation of the shortest path was very fast. I just computed and I didn't went much deep. I went for the neighbors and for their neighbors, but when I went for their neighbors, everything was already computed, so I finalized very fast the search. Sure, once you found all the paths, you may stop. I showed you the algorithm, but you can check, and if you already found all the paths, you can stop. But usually you will not stop because you don't know. Rarely you have a connected graph and you find so fast all the connections. Usually the optimization is not so big if you stop after you find all the connection, because sometimes you cannot find connections if its graph is not connected. You don't know that, and you need to search for all the neighbors to be sure that you have all the connections. Now, these were the algorithm executed step by step.